dark matter.
Yes.
What we call dark matter is ordinary matter in another universe whose gravity is spilling into our universe. There's some dimension going out of this universe into the next universe.
Has to.
And that's the dimension through which their gravity would leak.
It's basically this universal pressure that we're feeling from this other universe, and it's really just, for them, a leaky pipe.
This is StarTalk Special Edition, a Cosmic Queries variant on that. Why is it a Special Edition Cosmic Queries? Because we have Gary in the house. Gary.
Hey, Neil.
Where there's Gary, there is Special Edition.
So
because Gary is special.
Yes, as everyone knows.
Gary, always good to have you. Chuck?
Always a pleasure.
Back in the saddle.
That's right.
Doing some Cosmic Queries. And this is Grab Bag.
Grab Bag. Now, we used to call this Galactic Gumbo. Now, guarantee.
You used to call it that.
That's right. Now, come on down here. Now, put some little there. Get you some air toofy. And then we're going to move on down and get some of that little good gumbo.
You know who also was in the hood? Was all hail to the geek in chief, Charles Liu. All hail.
Oh, hail. Oh, you guys are sweet.
All hail to Charles Liu, visiting from the College of Staten Island of the CUNY system.
Yes.
Thanks for coming by my office here at the Hayden Planetarium.
Always so much fun to be here.
Do people know that he was involved when we opened this place? He was part of the scientific staff here that helped write exhibits and design things, and it's all there. So
very cool.
I just want to. We're now on our 25th anniversary of the opening of the Rose Center.
Wow!
And I just want to say thank you.
It was my pleasure. Thank you for giving me the chance to do it.
And we co-authored a book at the time called One Universe at Home in the Cosmos.
Yes, with Robert Irian.
With Robert Irian, that's right. He was a science writer. The three of us, and it was a celebration of how we were bringing science down to Earth in this facility.
So we got the band back together.
2/3 of the band back together. So this is a special edition grab bag, and I see we've broken it up into 3 categories. First one is black holes.
Yes.
But then the next one is just mixed bag.
Yes. And then the third one is more mixed bag.
More mixed bag. Thank you. Thank you.
Because we ran out of ideas.
Okay.
All right.
So we go straight in.
Yeah, kick off with the black holes.
The questions come from
our Patreon listeners.
Yes, and they are the only ones who have access to our question list.
Yeah.
Yes.
Right.
They get preference.
And it's only $5 a month. Someone wrote me and said, listen, I can't afford Patreon. Could you please ask this question? Because I don't have the $3,000 a month that you guys asked for.
I said, what?
Yeah, and I was just like, this is the wrong show. What show are you writing to?
Wait, what Patreon?
Yeah, and by the way, what show is that? Because I need to go do something for them. If they didn't Patreon people for $3,000 a month.
Amazing.
Oh, by the way, both Charles and I might know the answer simultaneously.
Okay.
But he's our geek in chief.
Science battle.
Yes.
2 scientists enter, 1 scientist leaves.
Never cross the beams. But I defer to Charles on so many counts.
Okay.
That I will sit here and just admire what comes out of his mouth. Okay?
That's easy to do.
All right, let's do this.
Having said all of that, we'll see.
We'll see. Go.
Yeah. Right. Tom Sturgill said, hello, Chuck, Charles, and Neil. He's in Florida. General relativity tells us that gravity is not a force, but a reaction of space-time to mass.
Okay.
Quantum theory tells us there may be parallel universes. Instead of dark energy, might we be seeing the effect of the mass of these other universes on our space-time?
Damn, we got badass.
What a great question to start.
Man.
That's excellent.
All right.
That's a well-thought-out question.
Yeah, it is.
Wait, does that mean we have to up our game if that's who's watching our show?
Yeah.
How do you want me to phrase this?
or is it that there's another astrophysicist out there just like, let's see them deal with this. Get these a-holes to see if they really know what they're talking about.
Okay, so start with the idea that is gravity really a force? I want to hear what you think about
that's
that.
Wonderful. Tom, you're absolutely right that the general theory of relativity is a supersedent theory that includes, I should say, Isaac Newton's original universal theory of gravity. And that is that on small scales, like scales of the Earth, scales of a solar system, for example, You cannot tell the
Small
difference.
things like the solar system.
Yeah, exactly.
You cannot tell the difference between acceleration and the curvature of space-time gravity.
Gotcha.
So they will look almost exactly the same. And they should look exactly the same on very small scales. So there have been experiments done to show whether or not gravity is a true force or it is truly a curvature of space-time. And so far, the two of them follow that so-called equivalence principle. So
So it's both.
it
Right.
is both on the scales.
circumstantially.
Right, in the circumstances that we are.
Circumstantially, they're both.
The exceptions come in extreme environments when you're not looking at sort of Earth-like or local environments. One example is a black hole.
Right.
Where you might indeed have a circumstance where you can tell the difference between a gravitational activity, curvature of space-time gravitational activity, and a force that measures out exactly like that curvature.
But how much of this is just semantics? Like, who cares whether it's curvature or Newtonian?
Oh.
If it accelerates an object,
Right.
and let that just be the force.
Right.
Why are we even bickering over this?
It matters because when we are trying to understand these extreme situations, such as a black hole or the beginning of the universe, there are subtle differences that do come into account, and you have to take them into account in order to get the science right. Okay.
Otherwise, you get the wrong answer.
Get the wrong answer.
Very good.
Right.
Okay. So but then we learn, if you take physics class and
Yes.
chemistry, about these other forces: electromagnetic,
Yes.
the weak nuclear force, the strong nuclear force.
Yes.
And then, we add gravity as a fourth force there, but
Right.
you're saying we shouldn't add gravity?
The problem is that gravity is creating that very strange boundary condition. The standard model about particles that we use, the quarks and the leptons and things like that, do not include a particle that moves gravity around. So if gravity is a fundamental force, there should exist a particle
We expect there to be.
called
based
a
on-
graviton.
Based on our understanding.
Because
we've
all other forces
forced.
have these mediating particles. So a graviton must be detected. But
Wait, hang on. So what propagates the electromagnetic force?
the photon,
And what propagates the weak force?
the W and Z particles,
That's obvious. And what propagates the strong force?
gluons.
Gluons. So there ought to be, keeping in the tradition of this sort of standard model of particles and their associated forces, the gravity should have a particle associated with it. And what would that be?
The graviton.
Graviton.
Yes, that's right.
Photon,
Gluon.
gluon, graviton, and
The
vector
intermediate
boson.
vector bosons.
So now let
Yes.
me ask you this, though.
Sure.
Photon has no mass, right?
Correct.
Okay.
None of the
No, does a
ions-
gluon have a mass?
Gluons do not have mass either.
How about Y and Z?
Actually, the W and Z particles
W and Z.
do have mass.
Yeah, that's
Yes.
there you go.
What?
So
What?
That is the
tell us why
fascinating part.
what's going on about that?
These particles
did
are
his
still
homework.
being studied. We're trying to figure out what they are. And well, you know what? Maybe the concept of mass is in itself worth talking about for a moment, because mass and energy are equivalent.
Right.
You can switch back and forth between
Absolutely.
them. So when we say we have a massless particle,
Right.
we're not saying that it has nothing. We're saying that it can carry energy, which can be converted into mass under the right conditions.
Right.
So a photon, for example, can have as much energy as a baseball. Some of the
course.
most powerful photons.
Right.
But they won't measure on a scale.
A baseball thrown by a pitcher.
Yeah, right. So
Not just a baseball.
yeah, that too. Well, E equals MC squared, right?
Implicit in
Yes.
your statement was
That's right.
it's a baseball thrown at 90 miles an hour.
Yeah.
Yes.
So you have this huge amount of stuff that's there, even though there is no mass.
Gotcha.
So given that,
So
one of the mysteries of the standard model and how our subatomic universe works is indeed what has mass and why, and what doesn't have mass and why.
right.
And how much-
So can you call energy potential mass?
You could.
You could
Yes.
call it that.
Yes.
Okay.
But what happens now, we have to bring in Tom's concept of quantum physics, right? General relativity and quantum mechanics have a real hard time connecting with each other. When you try to use these ideas of particles to explain gravity or the motion of things, you get stuck. The theory, the math doesn't quite match. And so this speculation that Tom has about, hey, is a black hole which has general relativity, whatever, could it be affected by quantum physics and this idea of, in this case, the many worlds interpretation? Could it be? It could, but the math doesn't show it yet. So this is actually a frontier that we're trying to wonder. some folks have speculated that you could actually use quantum physics to communicate within black holes. So you go from the interior of one black hole and be able to transfer to the interior of another black hole.
Right.
But it still wouldn't translate out
I was gonna
into
say,
our universe.
How would you ever find out?
Right.
Because you can't get any
That's
of the
right.
information
So-
out of the black hole.
So the math works in these
What
speculative
happens
ways.
in a black hole stays. in a black hole.
As far as we know, right?
The Cosmic Fight Club.
It never gets mentioned.
We don't talk about the event horizon. Yeah. So
Fight Club.
stay tuned, Tom, is what I would say. Odds are what you just speculated is not the case, but mathematically, people are still working on ways to make it possible. And then we have to figure it out. We have to test it to see if we can make these predictions actually manifest in observation.
Do you think the day will come where we'll discover a graviton?
Yes. We're pretty close already.
Okay.
The reason we're close is because of the gravitational wave detectors that we
Right.
found, right? There are some people making calculations and saying, well, if gravitational waves actually do exist, which we have now
Which
shown
they
they
do.
do, then there must be a graviton.
Right.
So the implication that gravitons exist is there. Now it's a matter of actually detecting one. And that is the bugaboo. The graviton is so low energy.
Right.
And there's so many of them
Right.
that being able to pick one out or to have enough data to show that these particles actually exist is extremely difficult.
That is wild.
Yeah.
All right.
All right, man. Wow. I wish I spoke math.
You do just fine.
Let's go to Parker Mann. And he says,
Parker Mann?
Parker Mann. All right, Parker Mann. Greetings, Dr. Liu, Tyson, Lord Nice from Ventura, California. Parker Mann here, thinking about colliding black holes. I wonder what happens just prior to the merger of the event horizons. Consider a binary pair of black holes slowly spiraling towards each other. Assuming the original stars were formed at the same time, they would have the same sense of rotation and revolution about each other. This would include the frame dragging around each body. Just before the horizons merge, the region between them will have a collision of sorts, as the linear motions of frame dragging will be in the opposite directions. What effect would this confluence of opposing frame motions have? Might the stress on space-time increase Hawking radiation temporarily, or even possibly trigger vacuum decay if the holes were massive enough? Man, let me tell you something. First of all, don't be trying to get us to do your advanced physics homework. That's number one, all right? Number two,
Make your question shorter.
exactly. Holy crap. First of all, this is somebody who studies astrophysics.
He knows Tom.
Hands down.
Tell us what frame dragging is.
So, what's the deal?
Yeah.
Frame dragging.
Frame dragging.
Very
Colliding black holes,
very
frame
simple.
dragging.
Yes. As you get closer and closer to event horizon,
Right.
and as you're moving,
Right.
your time sense, the dilation,
dilation
of it
of time.
becomes very visible.
Right.
So when you're in one direction, compared to the other direction of rotation or motion or whatever you have, you'll actually wind up with a different view of the same object.
Right.
And that's sort of the basic general concept.
it's all
of
about
frame
frame of
drag.
reference.
That's right.
It's all about
because
frame
your
of
frame
reference.
of reference is being dragged by the gravitational
Exactly.
curvature of space-time.
But wait, I mean,
Sure.
I think you have to show people what you're talking about, because I don't think people understand when black holes, you're actually talking about something that is tangible but not tangible, and they're moving towards each other.
That's right.
And they do this
As they
thing.
spiral around and around and around, and then they hit each other, right?
Right.
Just
Now-
to be clear, hardly ever in the universe are two objects falling towards each other on exactly the same line
Right.
for a collision.
It's not like two trains on the same track.
They're not right.
It's not
exactly.
like that.
Exactly. So there's always some non-alignment, and when there's non-alignment,
That's
you
when
have
a
the
spiral
opportunity
happens.
for
That's
spiraling
right.
in.
That's right.
Gotcha.
Correct.
So this question, which Parker Man has done. Wait, is Parker a new superhero? Parker Man. Anyway, as Parker is saying here, Parker, you're saying it exactly right, right? You're wondering what the interaction is between two black holes as they spiral closer and closer. And the answer is gravitational waves. You get gravitational waves released, and you get this energy that comes off. And the way that the black hole collides does lead to differences in what kind of energy gets released and in what quantity and in what direction and things like that. So your question, the answer, the very short answer to that question, Neil, you can tell me if I'm wrong, is yes. Okay, to all those things, those are all possibilities. And then which individual collisions cause what kinds of things to squirt out, that is still a subject of intense research.
And up to the geometry of what's going on.
Yeah.
But also, he did comment on something that I wish were true, but it's not the betting person's odds for it to be true.
Right.
That the dark matter,
Yes.
what we call dark matter, is ordinary matter in another universe whose gravity is spilling into our universe.
Right. That was Tom's concept, right?
Yeah.
Yes.
Yeah. So I'm all for that, even though I know dark matter is probably some more exotic particle.
That's right.
But that wasn't directly related to the black hole question. It was just a side point.
It's a thing that would be cool. But like you said,
very cool.
There's some mathematical possibilities.
Well, it opens up so many.
What I learned talking to Brian Greene about, was it Brian or the other Brian? We had Brian Cox.
Brian Greene.
Yeah, I hang with both.
Brian May?
Brian May as well. Yeah.
Oh, wait, that's Freddie. Sorry.
Oh, yeah, just the guitar, I think.
Yeah.
Did he follow what we're talking about? What? Brian May of the group.
The guitarist
Please.
for Queen.
For Queen.
Really?
Okay.
You had to ask?
He has a PhD.
I know he's a physicist.
PhD in
I'm just
astrophysics from
verifying that
Cambridge.
you're in this conversation
Yes.
that Charles and I are having.
Yes.
Brian May of Queen,
Is an astrophysicist?
has a PhD in astrophysics.
And Brian Cox.
Earned
Yes.
after Queen
Disbanded.
disbanded. That's
Yeah.
correct.
Queen hasn't technically dissolved, guys.
Okay.
Queen just keeps bringing in guest
Yeah,
vocals.
exactly.
Okay.
Yeah.
But yes.
Like Foreigner.
Yes. Right. But
So what I learned from him, which made complete sense, is for every dimension you add to the strength of a force emanating from a point, the strength of that force is diluted by the power of R to that dimension. Okay? So, in other words, if it's just flat, you can ask, how quickly does a cone spread out? And that goes 1 over R.
squared, if it's flat, the area of
it's
the cone
flat.
grows as 1 over r.
No,
squared.
there's no area. There's just the surface. It's just
I
the
see.
perimeter.
Yeah, sure. Yeah. If you're talking perimeter.
Yeah, it's just the perimeter. That's the strength at the perimeter. So on a flat surface, the strength drops off as 1 over R.
Gotcha.
If you are
Volume.
so that's 2 dimensions, right? And in a 3-dimensional volume, the strength drops off as the surface of the sphere gets bigger. That's R squared. If you have 4 dimensions, there's some dimension going out of this spatial dimensions, going out of this universe into the next universe.
Has to.
That's a higher dimension.
Right.
And that's the dimension through which their gravity would leak.
Right.
So
the power of their gravity would drop off precipitously
by the
at 1
fourth
over
power.
one
Yeah.
over the,
Oh, the
1
third
over
power.
R to the third power.
Third power, which is way faster
Right.
than ordinary gravity in this universe, which means that currently dark matter in our universe is 5/6 of the source of all gravity expressed in this universe.
Right.
Correct.
It's dominating this universe.
Right.
So it's already dominating this universe and it's dropped off by the third power of distance in a 4th dimension.
Which means we can never go where it comes from.
That's some hellified gravity in the other universe.
We can never go there.
Right. So I'm eating lunch and I almost choked. Eating lunch with, I think it was Brian Greene.
Yeah.
And it was like, wow, I had not thought of that. Because it has to come out of their dimensionality into this other dimension to reach us. And
If that's the way dark matter works.
If it works
Yeah,
that
but
way.
he's a particle.
That's really cool, though.
Yes.
That's kind of
Well,
cool because it's basically this universal pressure that we're feeling from this other universe, and it's really just for them a leaky pipe.
So,
Man, my bathroom has got water all over the floor,
Someone
and
plug
it's
that
messing
hole.
the whole universe.
Boy, I hope they don't because we all
Yeah,
fly
I
apart.
know.
Oh my gosh.
what if that can come through? What else
So
can come through?
I'm not an expert on where in quantum physics you learn just how all these forces propagate, but I am told by those whose knowledge I trust and value that the other forces cannot exit their space-time, but gravity can. and it's been explained to me more than once, and I try to follow, and I just nod.
Well,
but they said it very casually. It's not like, guess what? It was like, of course, the people in the know this.
For Parker and for Tom also, I would recommend you look up something called Randall-Sundrum theory, okay, which suggests that gravity's leakage from another space-time dimension could indeed lead to the things that we're talking about right now. Lisa's book.
So Lisa Randall, so she wrote a book called Warped Passages, which is an exploration into higher dimensions.
Very cool.
So, she's a friend. She's a contemporary of ours. We came up together in graduate school.
Oh,
awesome.
Not me.
So she's a professor up at Harvard, the Department of Physics.
The stronger gravity moves or migrates to
our dimensions, our space-time
like
becoming very weak.
Yeah, okay, but it's
More of like
it gets biological.
More of like a tunneling rather than a diffusion.
Yeah, that's better.
But to be continued. Yeah, guys, look it up. It's really kind of cool.
That's very cool.
Let's jump into our mixed bag.
Okay.
Matt Coda.
Mac Coda.
M-A-T.
Oh, Matt?
Yes.
Like a floor mat.
Yes.
I
From
mean, no
Paris,
disrespect,
Paris, France,
Matt.
rather than Paris, Texas.
Okay.
Did he say that?
Yes, he does. So I was going to give him the credit for it.
Did he not think that we're cultured enough?
No, I think he wants
know
to
that
make
there's a Paris across the ocean.
Well,
I think he
mean,
wants to make the difference plain.
Listen, if you're in France, believe me, you don't want to be associated with Texas in any way. Let's be honest. You know? Texas.
Recent supernova data is revealing something mind-bending about our universe. Instead of mysterious dark energy, scientists found evidence that time itself flows at different rates throughout space. Faster in the vast empty voids, slower where matter clumps together. I think that's a scientific term. Like Einstein's time dilation, but on a cosmic scale, are we witnessing our generation's Copernican moment, where our basic understanding of the cosmos needs to be rewritten? If this new model is right, what does it mean for the fate of our universe?
Interesting.
Wow.
Yeah, Charles.
I have not read.
Get us out of that.
I have not read those papers. So I cannot tell you whether it is actually a Copernican revolution right now or not.
What I think he's referring to is that may be a way to interpret the data, but another way was that Einstein's cosmological constant can vary from one time in the universe to another.
Right.
Whereas in his equations, it is a
Constant.
Okay? So something has to give here. And
Well, in his original equation, it was just lambda, right? But lambda as a function of time has been built into equations after he first proposed it. So lambda of t is certainly something that is mathematically possible. Whether or not
but his theory did not allow for that. So if his theory is an accurate description of the world, then what we're saying is then the world can have a time-dependent lambda. And if the world does have a time-dependent lambda, then his theory is not complete.
he knew his theory was not complete when he designed it.
That's true.
That's the whole point. Yeah. This is, I think, exactly what Mutt is describing, right? Is it time to supplement a long-standing theory with something new, right? And so whether it's a Copernican moment or not, I think there are probably other interpretations that would be simpler to follow Occam's razor and not necessarily have to require brand new physics.
Gotcha.
Right? For example, if we have a big clump of matter, we know that it acts like a gravitational lens, right? And gravitational lensing will cause, for example, the light coming from a distant object behind the lens to appear to have curved around it, right? And so that result could much more easily explain these observations of these supernovae, that it's more a gravitational lensing effect or some more complicated thing that we don't understand than the need to bring in a whole new varying cosmological constant kind of physical
And I would add a point that recently in an explainer that I did with Chuck, titled On Being Wrong, where Copernicus himself was wrong.
Sure.
And you have to ask, well, do we throw out the entire idea that the sun is in the middle of the universe, or do we look for some adjustment to this basic idea? And 50 years later, Kepler would discover
ellipses as opposed to
perfect circles. And so there are aspects of his idea that needed modification without throwing out the whole idea. So I'm with Charles on this, that it could be an important scientific moment, but not on the scale of a Copernican moment.
So, Matt, even if you are wrong, that's not necessarily bad, right? This is I think what science helps us understand. If we understand that science is a process of learning what's right and wrong, we're not demanding that I am right, you go home. But rather, I'm right in this aspect, you're right in that aspect. And together we reach something that's more complex than either of us could have achieved.
We are the world.
Yeah.
We are the children.
Excellent.
They're singing again.
And by the way, the fact that this person, his name?
Matt
who wrote us from Paris, France, means he, as a Parisian, presumably, has not been offended by your imitations of Parisians, of French people.
Well, let's hope not. Because, quite frankly, my bad imitation of French people is pretty spot on.
Ooh la la.
And 100% of them are smoking a cigarette.
Yes. The French have the best lungs in the world.
Apparently.
Because they can all withstand smoking, My lungs are so obnoxious that the smoke does not stand a chance.
Sorry, Matt. Sorry about that.
Okay, I'm sorry. That was funny. I don't care what y'all say.
That was funny.
That was funny.
That was funny. Dude, we're taking too long to answer these questions. Let's speed it up.
All right. Okay, here we go. This is Trisha Lynch. Hello, Dr.
Wait,
Tyson. Trisha Lynch.
Yes.
And she says, hello, Dr. Tyson, Dr. Liu, Lord Nice Gary. Trisha from Beaverton, Oregon here. If there really is life under the water of Europa or one of the other moons, will there be any way for us to observe it without possible cross-contamination?
Yes. You probably have more about this than I do.
Well, we did a whole episode on the Europa Clipper mission.
Right.
we did.
It's in our archives. Check it out. Mm-hmm.
Yeah, NASA has an Office of Planetary Protection.
Correct.
And its primary goal is to make sure that cross-contamination does not happen.
By saving us from Thanos.
For example, there's a very famous short story, award-winning short story written by physicist David Brin called The Giving Plague, where we bring back a pathogen from Mars.
Ew.
Not The Giving Tree by
Shel Silverstein.
By Shel Silverstein.
Right, different book. The number one most important thing is to make sure that our spacecraft don't crash. Right, we want to make sure that their orbits are solid, that they have enough boosting situation, and at the end of the mission, we dispose of the spacecraft in a way that will not contaminate any potential environments. This is what happened with both the Galileo space probe and the Cassini space probe around Jupiter and Saturn, respectively.
But we crashed Cassini purposely.
And we crashed Galileo purposely as well.
And did we?
But we crashed them into the atmospheres of Jupiter and Saturn.
In
and
such a way that we know that they would all burn up?
Oh, yeah,
exactly.
completely.
Instead of landing
vaporized.
somewhere and contaminating the space, they would all just be burnt up. Yeah,
We're not so careful about our own space junk,
sadly,
are we?
no. We have an issue in our local near Earth orbit ecosystem. We are quickly approaching the point where astronomy being done from Earth is being very badly affected by all of the stuff that's going on.
Because you get a bunch of reflections and a bunch of crossings and
streaks, all kinds of things.
All kinds of terrible things that mess up your information.
That's right. It makes it quite difficult. But fortunately, that is not yet the case as far as we know in places like Europa. So once you make sure your spacecraft isn't going to crash, the next thing you do is you find remote sensing strategies. So for example, we can look through the ice on the crust of Mars to see what's down there. Mm-hmm. Right? So we can, in fact, do the same thing without landing something on there through things like the kind of radar that we
crust
use.
Of Mars are you talking about? What are you talking about, crust of Mars? What are you talking
There's ice.
I mean, at the poles?
At the poles,
Okay.
yes.
Okay.
In fact, there are continents full of ice. There's a lot of it.
So
there.
ice-penetrating radar.
Yes. Yeah. Mm-hmm. So in the same way that we have here, even our weather radar,
now, can
which
we see the
penetrates
big
clouds.
machine that melts the ice that made the former Martian atmosphere? Are we able to see that?
If it's there, we could see it. If it's there, we could see
The Martian technologies.
Yes, exactly.
Right. Yes. No, well,
we have to start the reactor.
Let's get to the chopper.
Total recall. One of the most traumatic science fiction movies I've ever seen. But the book about that, right? We can remember it for you wholesale, written by Philip K. Dick. That's kind of a cool book to read sometime.
Why do you know this?
Exactly. That's so wild. So
We
wild.
only just know the movie.
It's a thing.
Charles knows things.
Okay, fine.
All right.
I have to remind. That's why we have him on the show. Okay. Did we answer the question? Was it?
Yeah, man.
Well, the answer you
She's like,
gave.
is it possible to do it without cross-contamination?
Oh, yeah, so
the
with-
fact is, we've already done it.
Wait. So with the ice-penetrating radar, it probably won't see microorganisms, but if there's a macroscopic fish, it'll see it, right?
That's right.
Yeah, okay.
And then therein lies the next point. Let's say we do find beautiful blue whales or something, you know, or gigantic whale shark fish type things down there. What do we do next? How do we study them and communicate and so forth? Right. Are they edible?
That is not my first thought, Charles.
Then the Office of Planetary Protection really has to think hard. Are we going to put a submarine, right, that goes down there? Do we want something that goes below the surface? And in that case, how do we protect the ecosystem?
And
do we have any idea?
And the good thing about Europa is the ice cracks, water comes up and refreezes.
Freezes.
So there's a suggestion that if we just pitch tent on the surface,
Let it slowly sink in.
no, we could dig up some of the material that came up and froze, and then
We
thaw
could
it out
analyze
and
that.
possibly see
Right.
Right.
a
Without
microorganism
having to cause
or
problems
fish that
anyway.
happen to get caught up in it. And
We could do what we do in Alaska, and that is cut a hole and just drop a pole,
Yes.
a line.
what do you mean we do? And what you Inuit? What, we do like this? Something like you do this?
May have done.
I'm just saying.
So, hello, Dr. Tyson, Dr. Liu, and I am assuming Chuck and Gary, and assumed you have. Right. I am Lily Rose from Virginia. My question is, what data can the recent probe flying close to the sun give us? How can we use this mission in the future to explore the nature of other stars in our galaxy? I was very curious about the goals of this mission. Thank you all for that and all for what you do.
Love
Lily
it.
Rose,
Great
thank
question.
you. Great
Yeah, yeah.
question.
That is a great question.
Did you do something about the Parker Solar Probe recently?
We did an explainer on it.
Yeah.
But it was more just to put it in context for people who've never heard of it. I don't know how deeply we went into the science that would come of it. We just know that it went faster than any previous spacecraft, closer to the sun than any previous spacecraft, got hotter than any previous spacecraft. It's going to study the solar wind, of course, solar flares, the particle fluxes, this sort of thing.
I see. Well, solar science has a number of amazing questions, which surprisingly we still don't know the answer to, even though the sun is so close to us, right? Only 93 million miles away. One such question is the transition from the surface of the sun, the photosphere, which is about 11,000 degrees Fahrenheit, out to the
11,000
yeah,
degrees.
11,000.
He just started here.
Yeah.
Give him a chance.
Out to the corona of the sun, which is millions of degrees.
Millions.
Right. It has to actually, you'd imagine that the further away you get from the sun, the colder it gets. But no, after it gets colder and colder and colder, suddenly, right in that boundary,
I would
roughly
say
where the
actually it
Parker...
gets less and less and less warm.
Okay.
Not cold. There's no part of
take
the
it.
sun that's cold.
Fair
okay?
enough, fair enough.
All right.
As you get to that boundary, suddenly, right in the area where the Parker Solar Probe is starting to probe, it has to heat up again. What energies are being transferred? What kinds of mechanisms are growing your temperature again from 10,000 to millions?
So now wait, is there a cooling or is it literally we see a decrease in temperature?
Yes.
Then all of a
To the
sudden
surface.
To
From the
the surface and
center.
then from the photosphere, but
Yes.
then we get to the corona and all of a sudden it heats.
That's right.
Between the photosphere,
Between this photosphere and the corona.
Right.
Now, but is there any reaction that we can like identify that might be making something like this happen?
There
Hence
are
the solar probe.
there there
about
are
that?
Oh my God, I came up with an idea. Why don't we send something to investigate?
That's right.
Is this temperature change completely around the circumference, or is it isolated pockets?
Piece by piece.
Really?
It's kind of like an envelope, but the envelope has holes in it.
Right.
So it's inhomogeneous, heterogeneous, shall we say. And also, there is actually a layer there between the photosphere and the corona. It's called the chromosphere. And that area is
forgotten about
very mysterious to us. So all of our hypotheses here on Earth about how that heating happens and what the energy transfer is from the surface of a star out into space need to be tested with data. So the Parker Solar Probe helps us understand how stars transfer that energy outward. And that affects everything that's orbiting those stars,
Yeah.
such as planets.
which NASA calls space weather, right? And so just to put a little molecular talk in here, so temperature is the average vibration speed of molecules. So you get to the surface of the sun, and there they are vibrating. And now something happens where now they're vibrating faster.
Right.
Okay, so something's flinging them out. Some energy source is pumping it. But the corona is very rarefied. So would you, holding aside the radiation of the sun itself,
Sure.
if you're in a bath
Yeah.
of 1,000,000 degrees with only like a molecule hitting you
Right.
here and here, what would that feel like to you?
It wouldn't feel like much. The irony is, although the temperature of the corona is millions of degrees, if you put a potato in the corona, it really wouldn't bake, because the amount of heat in this plasma is tiny per unit volume. So in the volume of a potato, you wouldn't actually have enough heat in there to bake the potato. But with the energy flowing through it over long periods of time, you would fry that potato and dissolve it into atoms like in due course, because the energy is flow is strong. The energy density is low. And so these are the kinds of contradictions that we need to get data on that the Parker Solar Probe can help us understand.
And just so we're on the same page, a cup of coffee is hot, but an iceberg has more heat, more total heat.
Then a cup of coffee.
Because the heat is the total added vibrational energy of all the molecules. Right. And a cup of coffee, you put a thermometer will read something different, but the total energy is different.
Gotcha.
Okay?
How are we getting information back? Because
it gets transferred through radio and things like that.
Okay, so
Oh, it's got a shield, by the way.
Yeah,
So
so-
I said it got hotter than anything before. The shield actually keeps the electronics quite cool.
okay, so what's the time?
8 minutes.
Only 8 minutes.
And 20 seconds.
Of course.
Because it's the same as all light.
Pretty much.
It's a
Yeah,
regular-
yeah.
Exactly.
Yeah. 8 minutes and 20 seconds
Is
equals how many seconds?
I don't know. I'm not going to sit here and
500 seconds. So it's a nice round number.
That's cool.
Yeah.
all right.
Just so you know.
I'm better for the knowledge.
Now you will never forget that. Yes.
My word. Thank you.
All right. This is Alexander Samolenko. Alexander.
Sounds Ukrainian.
That sounds Eastern Bloc.
Listen, he says, hello, Dr. Tyson, Dr. Liu, Chuck, Gary. I'm Alexander from, Kyiv,
Hey,
Ukraine.
Charles
good
is
one.
on the case
Charles,
here.
it was
you're
a
killing
wild guess.
Well, I just said Eastern Bloc. That's all I said.
Right.
Yeah.
He says, here's my question. Can it be that our entire universe exists in its own time loop? Big Bang happens, then we appear, develop science, find out all underlying building blocks of the universe, then ignite a new universe when this one starts to fall apart. Let there be light, as a matter of fact. So our universe is sort of a gin particle.
Let me point you, Alexander, thank you for this great question, to a short story written by Isaac Asimov that Isaac himself said was his favorite amongst everything he wrote. It's called The Last Question.
The Last Question.
Yes, and this was Isaac's
good
own
one.
way of trying to figure out this very question that you described. In fact, cosmologies all throughout the
Tell
world.
us the story.
No,
By the book.
it's a short story. It's very quick. I'm not going to spoil a single thing about that
We
story.
gotta,
It's that good.
now you got to go read. Look at this.
Okay,
that
it's a
good.
brilliantly written, clean story. By the way,
Look at Chuck Liu giving us homework.
I
Can't believe
It's the professor in me. I'm sorry, Chuck. It's how it goes.
I'm trying to sneak out the answers here.
Nope,
He's
nope,
like,
nope,
He's
nope, nope.
slapping me down.
Nope, nope.
So Isaac Asimov, I don't know if you know, he never flew anywhere for whatever reasons. And he was a native New Yorker. If you ever heard him speak, that would be obvious. And he was a friend of this museum.
Yes.
In fact, most of the research done on his physics, astro, and biology novels and nonfiction books were researched out of our library here at the American Museum of Natural History.
Very, very.
And
And we have an annual panel debate in his honor, the Isaac Asimov Memorial Panel.
And let me give a shout out to his late wife also, Janet Jepson Asimov, who was a writer in her own right.
Yes.
Wow.
Yes.
Look at that.
Yeah.
So what's the deal?
The deal is
Could we
very
be a
simple.
gin particle?
We could, but we don't have the evidence to confirm that yet. This is a speculation that's gone on in cosmologies all around the world for all of human civilization.
Yeah, but how would we end?
I don't know.
Unless we recollapse and then start
Well, we
again.
wouldn't end.
We need
That'd be
new
the
Right now,
point.
it doesn't.
The point is we need new physics, right? The physics as we have it,
You're not
if it's
happy with the
complete.
physics we already
Oh, I'm
produced
very
for you?
happy with it, but I also think it's incomplete. If there is no more physics to be had about the expansion of the universe, it will just go on forever and that's it. But if there
To
were...
the big rip.
That's right.
Scary.
But what if there were something else, and we're not sure that that's the case yet, right? If there is something like vacuum decay, which I know it's just a word I just threw around, I'm so sorry. The idea that our vacuum energy level in the universe is a false vacuum, and in fact there is still energy hiding in there, and some cataclysmic event could cause that
collapse
energy
of that
to be
vacuum. Ooh.
released.
We have a rift.
This is all physics that has mathematical roots, but does not have experimental verification.
In Cosmic Queries, a StarTalk book, there's a whole section on this very topic.
That's right.
And
There
it's
is.
very spooky
It's
and
very,
scary.
very cool. It's not spooky and scary. It's cool. I think it's really neat. The possibility of it happening anytime in our lifetimes or even in the human species lifetime is minuscule. But the chances of it happening eventually, that's non-zero. And imagine if that is the way that our universe reignites itself. In fact, if the conditions before our Big Bang were such that it happened before, and this continues depending on the state of the universe, energy densities, matter densities, whatever, then indeed, this particular idea of a cyclical universe that continues and comes back, each time being a little bit different than the next time, but with the same laws of physics, Alexander, you're not that far off from what a lot of theoretical physicists are thinking right now.
I would add that I want to give a little punctuation to his comment about this false vacuum. If you have a puddle of water sitting in
A puddle.
Thank you. No, so you have like a ledge and then a little sort of depression there,
Right.
and another ledge over here. So there's an area where water collects.
Okay.
You can say, is that the lowest energy state the water can be in? Well, on the other side of this ledge, it can get lower. So we can be living in here thinking we're stable,
Right.
but that's not the most stable configuration of that puddle. The most stable configuration of that puddle is
It's
the
to
entire
seek
puddle.
that other place.
Just this other
That's
place.
right.
The lower part.
The lower part.
So
Right.
in the quantum construction of the universe, it is possible for this puddle to tunnel through this barrier and then spill down and occupy this next place.
Right.
And the state of our universe is not at a stable base. There's for me, a fear factor that we can end up tunneling into some other place that has whole other rules and other, I don't know what'll happen. We all die.
Right. Somebody's draining the pool.
Let me just make sure everyone knows that 2025 has been designated the International Year of Quantum Science and Technology by the United Nations. So
Well, your
this
book
is
came out just in time then.
it did.
The handy quantum physics
answer book.
answer book.
Yes.
One in a series of three. You're like their main guy. You have one on physics,
Not
and
main guy,
astronomy,
there's-
and
quantum
physics.
physics.
Came out
Yes.
just in time.
Yes.
Okay.
So everybody, please enjoy this conversation we're having right now. I hope it's just the springboard of you all going out and checking out more of this.
So
cool
why is
stuff.
it this year?
It's the 100th anniversary of what most people designate as sort of the firm foundational birth of quantum physics.
The
as
whole
we know it today.
1920s, but you slap it right in the middle.
Yeah.
And you've got
You've got the origin.
You've got the origin story of quantum physics. Charles, good to have you, man.
Thank you so much. It's always a
Oh, my
pleasure. It's so
gosh.
great to talk to everybody, and your questions
you
are
go.
marvelous. I love that.
I just bought your book.
Dude, thank you.
I just bought your book.
Did you get one for each of us?
No.
Look at the camera.
I got one for each of you in the quantum. So you have to tunnel and get my book.
Thank you, Jeff.
Can you buy me a shovel?
Charles, good to have you, man.
As always, dude. Really appreciate
Love
it.
to the family, everybody.
Thank you. And you too.
Gary, Jeff.
Pleasure.
Always a pleasure.
All right, Neil deGrasse Tyson here for another episode of StarTalk Special Edition, this time Cosmic Queries. Till next time, keep looking up.